Okay, I'm back again, and we are going to do a little streaming for now. We are going to be live for around 40 minutes because then I have a lesson. Let's study something. We'll continue. Okay, so we were at the assignment operators. In C++, assignment of values to variables is built into the expression structure. The equals operator takes two operands just like plus or multiplication. The left operand must indicate a value that can change. That's true because that's a variable, which is typically a variable name. When the assignment operator is executed, the expression on the right hand side is evaluated and the resulting value is then stored in the left hand side variable. So you always need to remember that you will solve any expression from the right to the left side. The effect is that the value 1 is assigned to the variable result. Okay, that's simple. That is also simple. Assignments that are written as part of the larger expressions are called embedded assignments. Okay. Although there are contexts in which embedded assignments are extremely convenient, they often make programs more difficult to read because the assignment is easily overlooked in the middle of the complex expression. For this reason, this text limits the use of embedded assignments to a few special circumstances in which they seem to make the most sense. Okay. We can also set three variables with 0 by just saying a equals b equals c equals 0. That's multiple assignments. Then we also have shorthand assignment in which, like the plus equals and minus equals, multiply equals, divide equals, those things. We also have increment and decrement operators, x plus plus. So that's a unary incrementing operator to just add 1 into x. The same thing for the x minus minus, then you decrement 1 from the x. So that's increment and decrement operators. Okay. Then we also have something called postfix and the prefix. Postfix means x plus plus and prefix means plus plus x. So x plus plus calculates the value of x first and then increments it. The value returned to the surrounding expression is the original value before the increment operation is performed. So basically when you do y equals x plus plus, you're going to assign the original value of x to the y and then you increment x. But when you do plus plus x, you will do the incrementation of x first and then assign it later. So you will assign the incremented value. Right? That makes sense. Then the Boolean operators. The Boolean operators are all the relational operators to check basically the relation between two things. So these are used in the if-else conditions. We have double equals, not equals, greater, less, greater than equals, less than equals, all of those. Then we have logical operators, which are the exclamation, which is not, and then ampersand, that's and that's or. We know about that. That's fine. We can use a truth table to know about that. Yeah, the same truth table which we did in physics. Okay, we also have something called short circuit evaluation. So if you know that the first expression, we actually know this, so we're not going to explain it again. We have question mark colon. Okay, that's also a thing. It's like a condition. So you put the condition, put a question mark, put the answer according to that condition, then put a colon and then put another answer. Okay. Then we are on the statements. Right now we are at page number 32 out of 682. We'll see. So statements. There are two types of statements. Simple statements are just like an expression with a semicolon at the end, but a control statement is like checking a condition, and then based on that condition you do some statements inside it in the curly brackets. We can also have compound statements, which are to emphasize that there are statements as far as the compiler is concerned. Blocks are sometimes referred to as compound statements. The statements in the interior of a block are usually indented relative to the closing context. The compiler ignores the indentation, but the visual effect is extremely helpful. So it's just saying that it's not necessary for you to put any indentation, but it's good if you're putting indentation inside the curly brackets, because that's really helpful when somebody is reading your code. Otherwise, everything isn't just like the same indentation. That's really confusing and weird. So indentation is critical to good programming, so you should strive to develop a consistent indentation style in your programs. The only aspect of blocks that tends to cause any confusion for new students is the role of the semicolon. In C++, the semicolon is a part of the syntax of a simple statement. That's okay. This is very, very important. If you want to teach that where do you need to put a semicolon, then you can say that at the end of every simple statement you should have a colon. But if it's not a simple statement, it's a compound statement, or what was that called? Or if it's a control statement, then you don't put a semicolon at the end. In C++, the statements in any block may be preceded by the declaration of variables. Okay, this is all fine. It acts as a statement terminator rather than just a statement separator. While this rule is perfectly consistent, it can cause trouble for people who have previously been exposed to the language Pascal, which uses a different rule. In practical terms, the differences are: in C++, there is always a semicolon at the end of the last simple statement in a block. In Pascal, the semicolon is usually not present, although most compilers allow it as an option. In C++, there is never a semicolon after the closing braces of a statement block. In Pascal, a semicolon may or may not follow the end keyword depending on context. The convention for using semicolons in C++ has advantages for program maintenance and should not cause any problem once you are used to it. The if statement. In writing a program, you'll often want to check whether some condition applies and use the result of that check to control the subsequent execution of the program. So that's called conditional execution. The easiest way to express conditional execution in C++ is by using the if statement, which comes in two forms: if condition and then put a statement, if condition then put a statement, else another statement. Or you can also put else if. You can put more than one. You use the first form of if condition when your solution strategies calls for a set of statements to be executed only if a particular Boolean condition is true. If the condition is false, the statements that form the body of the if statement are simply skipped. You use the second form of the if statement for the situations in which the program must choose between two independent set of actions based on the result of a test. This statement form is illustrated by the following program, which reads in a number and classifies it as either even or odd. As with any control statement, the statements controlled by the if statement can be either a single statement or a block. Even if the body of a control form is a single statement, you're free to enclose it in a block if you decide that doing so improves the readability of the code. The programs in this book enclose the body of every control statement in a block unless the entire statement, both the control form and its body, is so short that it fits on a single line. Yeah, so we will always use a curly brackets if we are using a control statement. If we will just not use it if sometimes we are just having one line of execution after it. but mostly we will. We also have something called switch, which is very similar to the if else, but I don't really like switch. I don't know. We are gonna read that still. Let me check one thing. Okay. So the switch statement, the if statement is ideal for those applications in which the program logic falls for a two-way decision point. Some conditions is either true or false. The program acts accordingly. Some applications, however, call for more complicated decision structures involving several mutually exclusive cases. In one case, the program should do X, in other case, it should do Y, in third case, it should do Z, and so forth. In many applications, the most appropriate statement to use for such situations is the switch statement, which has the following syntactic form: switch based on this condition. If the case is this, then you put the statement break, and then case 2, the statement break, more cases, and then you put the default. The expression E is called the control expression. So you put the condition at the top, and then what is the value of that condition coming. Based on that case, you will put the statement, you'll break, statement, and break. When the program executes a switch statement, it evaluates the control expression and compares it against the value C1, C2, and C4, so forth, each of which must be a constant. If one of the constants matches with the value of the control expression, the statements in the associated case clause are executed. When the program reaches the break statement at the end of the clause, the operations specified by that clause are complete, and the program continues with the statement that follows the entire switch statement. The default clause is used to specify that what action occurs if none of the constants match the value of the control expression. The default clause, however, is optional. If none of the cases match and there is no default clause, the program simply continues with the next statement after the switch statement without taking any action at all. To avoid the possibility that the program might ignore an unexpected case, it is good programming practice to include a default case to just say unexpected value. The error function is a part of genlib library and provides a uniform way to responding to errors. This function takes one string parameter, the error message, and the error function does not return after the error message. It displays the program terminals. The code I've used to illustrate the syntax of switch statement deliberately suggests that break statements are required at the end of each clause. In fact, C++ defines that it's the break statement. Oh, so if we don't break after a specific case clause, then it will still be moving to the next part, like if condition. It's not if if you don't break. Makes sense. To reinforce the importance of remembering to exit at the end of each clause, the programs in this text always include a break or return statement in such clause. The one exception in this rule is that multiple case lines specifying different constants can appear together one after another before the same group statement. For example, a switch statement might include the following code, which indicates that the specified statement could be executed if the selected expression is either 1 or 2. Then you can put both the cases on the top of each other and put the expression inside it. The C++ compiler treats this construction as two case clauses, the first of which is empty because the empty clause contains no break statement. A program that selects the first pass simply continues on with the second clause. From a conceptual point of view, however, you're better off if you think of this construction as single case clause representing two possibilities. So you have the switch statement, you have a function, you have all the cases. Okay, that's a possibility. The code assumes that there is a function called leap year and which tests whether the year is a leap year and that the names of the month have been defined as constants as follows. Oh, that's a huge code. Why do we write it like this? I mean, we can write it so that it makes more sense to the user who just came in and trying to learn. Okay, that's fine. Then the constants in a switch statement must be of integer type or a type that behaves like an integer. The actual so in the switch type you can't put anything other than the integers. You can also put characters like a, b, c, like that, because that can also be converted to integers. But don't put something which can't be. The while statement. Okay, we are at the while now. I'm not sure how long this chapter is going to be. I don't think this should be too long. I should be able to complete it today. I can. It's 52 pages long and I'm on 36. Let's do that. So, while, as we already know, we check a condition inside it. If it's true, then we do something in the loop, in the cycle. The two most important principles about the operation of a while loop: the conditional test is performed before every cycle of the loop, including the first. If the test is false initially, the body of the loop is not executed at all. It will not even check afterwards if the test, first of all, is false. The conditional test is performed only at the beginning of a loop cycle. If that condition happens to be false at some point during the loop, the program doesn't notice the fact until a complete cycle has been executed. At that point, the program evaluates the test condition again. If it is still false, the loop terminates. The operation of the while loop is illustrated by the following function, which computes the sum of the digits in an integer. So you make the sum, you assign it to 0, you say while n is greater than 0, you keep on dividing it by 10, take the remainder, add it to the sum, do the division by 10, so you remove the last digit, and then you keep on doing that until the n is greater than 0. Then you return the sum at the end. The function depends on the following observations. The expression n divided by n modulo 10 always returns the last digit in a positive integer n. The expression n modulo 10, n divided by 10 returns a number without its final digit, because it will remove the last digit. The while loop is designed for situations in which there is some condition that can be applied at the beginning of a repeated operation before any of the statements in the body of the loop are executed. If the problem you are trying to solve fits the structure, the while loop is a perfect tool. Unfortunately, many programming problems do not fit this easily into the standard while loop structure. Instead of allowing a convenient test at the beginning of the operation, some problems are structured in a way that the test you want to write to determine whether the loop is completely false, most naturally somewhere in the middle of the loop. The most common example of such loops are those that read in the data from the user until some special value or a sentinel is entered to the signal at the end of the just replying to a message. Okay. When expressed in English, the structure of the sentinel based loops consists of repeating the following steps: read in a value. If the value is equal to the sentinel, exit from the loop, perform whatever processing required for that loop. Unfortunately, there is no test you can perform at the beginning of the loop to determine whether the loop is finished. The termination condition for the loop is reached when the input value is equal to the sentinel. Sentinel is just the word used for the last entered value, so it's not that special. In order to check this condition, the program must read in some value first. If the program has not read in a value, the termination condition doesn't make sense. Before the program can make any meaningful test, it must have executed the part of the loop that reads in the input value. When a loop contains some operation that must be performed before testing for completion, you have a situation that programmers call the loop and a half problem. when a loop contains some operations that must be performed before testing for completion. What do you mean? One way to solve the loop and a half problem in C++ is to use the break statement, which in addition is to use the switch statement, has the effect of immediately terminating the innermost. Oh. So basically, if in the loop also you want to check a condition, and if that condition satisfies, you want to break in between, or you want to continue or skip that condition, you can use break and continue for that. Note that while true line itself seems to introduce an infinite loop because the value of the constant true can never become false. The only way this program can exit from the loop is by executing the break statement inside it. So you should have a condition in which you have a break statement so that it settles down. Then we have a program they have, but I'm not gonna look at it. So we are on the for loop again, not again, now. So one of the most important control statements in C++ is the for statement, which is used in situations in which you want to repeat an operation in a particular number of times. The general form is this. So you write, yeah, we can compare it like this: int, init, test, steps. Init, test, and steps. Okay. The operation of the for loop is determined by the three italicized expressions on the for control line: init, test, and step. The init expression indicates how the for loop should be initialized and usually declares and initializes the index variable. For example, if you write for int I equals to 0, I less than something, and then like that, then the text expression is a conditional test written exactly like the test in a while statement. As long as the test expression is true, the loop continues. Thus, the loop begins with I equals to 0 and continues as long as I is less than n, which turns out to represent a total of n cycles, with I taking on the value 0, 1, and 2, and so forth, up to the value n minus 1. So it goes one value below. The step expression indicates how the value of the index variables changes from the cycle to the cycle. The most common form of step specification is to increment the index variable using the plus plus operator, but this is not the only possibility. For example, one can count backward by using minus minus operator, or count by twos by using plus equals to 2, or yeah. So you can put any kind of increment or decrement in a for loop. So you can do plus equals to 2, plus equals to 3, or plus plus just to add 1, and minus minus just to add, just to decrement 1. The C++ standard states that the scope of an index variable declared in the initialization expression of a for loop extends to the end of the loop body and no further. Some C++ compilers, such as Visual C++ 6.0, mistakenly extend the scope of to the end of the block, enclosing the entire loop. Generates the following sample run, which is looking good. Okay. The expressions init, test, and step in a for statement are each optional, but the semicolons must appear. Okay, each of them are optional. You can just put the start and do nothing else, actually. If init is missing, no initialization is performed. If the test is missing, it is assumed to be true. If the step is missing, no action occurs between loop cycles. Okay. Okay, let's move to the functions. I think I need some examples in which, like for loop examples in C++, with no init or no steps or no test and different combinations with output. So I want to know what it actually does. doesn't work. Wait, let me check. Okay, it's running it. Let me just wait until it gives me some examples. Okay, it gave me some examples. So if you don't have, okay, so if you have all three, then it's fine. If you don't have initialization, it's gonna, then you need to put the initialization at the top. Okay. If you don't have the stop, like the last value, then it's gonna go up till the end. So it's like infinite loop, but you need to stop it somewhere. So you need to have a break in between. Okay. Okay, I need to change my price. Let me do that fast. Okay, I'm done. Okay, so if we don't have any updation, then we need to update inside, otherwise it will not update anything. Okay, I understand actually. Hmm. Okay, let's move to the functions. We are at page number 40. A function consists of a set of statements that have been collected together and is given a name. The act of using the name to invoke the associated statements is called calling that function. To indicate a function call in C++, you write the name of the function followed by a list of expression enclosed in parentheses. These expressions called arguments allow the calling program to pass information to the function. For example, in the power_tab.cpp program at the beginning of this chapter, the function raise into int to power took two integer arguments n and k, which are the values it needs to know in order to compute n raised to the power k. If a function requires no information from its caller, it need not have any arguments, but an empty set of parentheses must appear in the function call. Once called, the function takes the data supplied as arguments, does it work, and then returns to the program step from which the call was made. Remembering what the calling program was doing and being able to get back precisely to that point is one of the defining characters of the function calling mechanism. The operation of going back to the calling program is called returning from the function. So we go to the same line where we actually called the function. Returning result from function, as the return functions can send result back to the calling program. Thus, when this function returns with the statement return result, the value of the local program result is passed back to the main program as the value of the function, and this operation is called returning a value. Okay, that makes sense. Functions that return Boolean results plays an important role in programming and called predicate functions. Functions, however, do not need to return a value at all. A function that does not return a value and is instead executed for its effect is called procedure. Oh, that's the difference between a function and a procedure. A function always returns a value, but a function which doesn't return a value is called a procedure, because that function is just used to do some effect on some variable or something. Procedures are indicated in the definition of a function by using the reserved keyword void as the result type. Let me see. Okay. So the data type for it will be void. The return statement in C++ has two forms. For procedures, you write the statement as return and just nothing after that. For functions that return a value, the return keyword is followed by an expression as follows. So you return an expression from it. Executing either form of the return statement causes the current function to return immediately to its caller, passing back the value of the expression, if any, to its caller as the value of the function. Function definitions and prototypes. A function definition has the following syntactic form. In this example, result type is the type of the value returned by the function. Name is the function name. Parameter list is the list of the declarations separated by the commas, giving the type and the name of each parameter to the function. Parameters are placeholders. Okay, parameters are placeholders for the arguments applied in the function call and act like the local variables except for the fact that they are given initial values by the calling program. Okay. If a function takes no parameters, that entire parameter list in the function header line is empty. The body of the function is a block and typically contains declarations for the local variables required by the function. Before you use a function in a C++ program, you declare it by specifying its prototype. A prototype has exactly the same form as the function definition, except that the entire body is replaced by the semicolon. The name of the parameter variables are optional in the prototype, but supplying them that usually helps the reader. The mechanics of the function calling process. When you call a function in a program, the following step occur. The calling program computes value for each argument because the arguments are expressions. This computation can involve operators and other functions, all of which are evaluated before execution of the new function actually begins. Okay, the system creates new space for all the local variables required by the new function, including the parameter variables. These variables are usually allocated together in a block which is called stack frame. Okay, wait. These points are somehow new, so let me just read them again. the mechan the not mechan okay the mechanics of the function calling process. When you call a function in a program, the following steps occur. The calling program computes value for each argument. Because the arguments are expressions, this computation can involve operators and other functions, all of which are evaluated before execution of the new function actually begins. The system creates a new space for all the local variables required by the new function, including parameter variables. These variables are usually allocated together in a block, which is called stack frame. So every function, when it is being called with all the arguments and the local variables assigned, initialized inside the function, we put all of them, we assign all of them a memory in, and it is called a stack frame. The value of each argument is copied into the corresponding parameter variable. If there is more than one argument, the arguments are copied into the parameters in order. The first argument is copied into the first parameter and so forth. If necessary, type conversions are performed between the arguments' values and the parameter variables, as in an assignment statement. For example, if you pass a value of type int to a function that expects a parameter of type double, the integer is converted into the equivalent floating point value before it is being copied to the parameter variable. The statements in the function body are executed until a return statement is encountered or there are no more statements to execute. The value of the return expression, if any, is evaluated and returned as the value of the function. If the value being returned does not precisely match the result type declared for the function, a type conversion is performed. Thus, if a return statement specifies a floating point value and a function return a list, the result is truncated to an integer. Okay. The stack frame created for this function call is discarded. In the process, all the local variables disappear. The calling program continues with the return value substituted in place of the call. Passing parameters by reference. Okay, all of this which we were doing, we were talking about the local parameters and they were getting all deleted once we are done with the call of the function, but this is all passing by value. We can also pass by reference. In C++, whenever you pass a simple variable from one function to another, the function gets a copy of the calling value. It doesn't get the same variable itself. So that means if it gets a copy, if you want to change that variable into the function, it's not going to change it outside. It has no effect on the calling argument. For example, if you try to implement a function that initializes a variable to 0 using the code, the function has no effect whatever if you call. The parameter var is initialized to a copy whatever value stored in x, and assignment variable inside the function sets a local copy to 0 but leaves x unchanged in the calling program. To address this problem, you can change the parameter to a reference parameter, and to pass anything by reference in C++, you use ampersand. By adding an ampersand to the parameter declaration in the function header, now the parameter value will not be copied. Instead, a reference is made to the original variable. Changes to the parameter are reflected to the original variable. The new coding is this, by using the ampersand. To use this function, the caller must pass an assignable integer variable. To set x to 0, for example, you would need to make the following call. Passing an integer constant such as 3 would be an error because 3 is not an assignable integer variable. The use of reference parameters makes it possible for functions to change values in the frame of their caller. This mechanism is referred to as call by reference. Okay. In C++, one of the common uses of call by reference occurs when a function needs to return more than one value to the calling program. A single result can easily be returned as a value of the function itself. If you need to return more than one result from the function, the return value is no longer appropriate. The standard approach to solving the problem is to turn the function into a procedure and pass values back and forth through the argument list. As an example, suppose that you want to write a program to solve the quadratic equation, but that because of your desire to practice good programming style, you are committed to dividing the work of the program into 3 phases as represented by the boxes in the flowchart. Input phase, accept the values of the coefficient from the user. Computation phase, solve the quadratic equation for those coefficients. Output phase, display the roots of the equation on the screen. Decomposing this problem into separate functions that are responsible for each of these phases is somewhat tricky because several values must be passed from each phase to the next. Because there are three coefficients, you would like the input phase to return three values. Similarly, the computation phase must return two values because a quadratic equation has two solutions. Figure 1 to 5 shows how call by reference make it possible to decompose a quadratic equation problem in this way. At each level, parameters that acts as input to each function are passed in the conventional way. Parameters that represent output from the function are passed as reference. Stepwise refinement, procedures and functions enable you to divide a large programming problem into smaller pieces that are individual is easy to understand. The process of dividing a problem into manageable pieces is called decomposition. It's a fundamental programming strategy. Finding the right decomposition, however, turns out to be a difficult part that requires considerable practice. If you choose the individual pieces well, each one will have conceptual integrity as a unit and make the program as a whole much simpler to understand. But if you choose unwisely, the decomposition can get in your way. These are no hard and fast rules for selecting a particular decomposition. You will learn how to apply this process through experience. When you're faced with the task of writing a program, the best strategy is usually to start with the main program. At this level, you think about the program as a whole and then try to identify the major pieces of the entire task. Once you figure out what's the big piece of the program are, you can define them as independent functions. Since some of these functions may themselves be complicated, it is often appropriate to decompose them into still smaller ones. You can continue this process until each piece of the problem is simple enough to be solved on its own. The process is called top-down design or stepwise refinement. So you go from top to bottom and then you solve. I'm almost done with this chapter because now I'm on the summary. But let me just go through a piece of code they have. Implementation of quadec.cpp that illustrates call by reference. So we are making these three functions, passing them, making all of them by reference. We are not returning anything, but we are just okay. I'm gonna look at it. So for now, let me just stop streaming. That's it because I have a lesson in 2 minutes. I'll see you.